All right. So, today we are closing out chapter 29 by talking about the magnetic force, which we've kind of done things backwards, right? When we talked about the electric force, we started with the force, then we moved to the field, and then we talked about some other things that go with it, right? In this case, we kind of did this in a little bit of a backwards way. We've talked a lot about the field, but so far we haven't actually discussed anything of how it creates a force. What creates the magnetic force? How do we actually calculate that out? And the reason that we've done that because it's a little bit more complicated this go around. Let's take a look. So, and let me get rid of that line right there. Magnetic forces act a little bit different. For what we remember from the electric force, we said, okay, well, a charge times the electric field gives us that force, and the direction by the direction of the electric field. Easy, nice. Magnetic field is a little bit strange. There's a cross product in here, which should hopefully not come as a surprise, because as I've stated before, every important magnetic equation has a cross product in it somewhere. But I want you to think about what that means. Particles don't follow the magnetic field. They don't feel a force in the direction of the magnetic field. They feel a force perpendicular to the magnetic field and perpendicular to the velocity. That means that if I'm thinking about something like work or potential energy, the magnetic field can't do any. It's never going to be able to do work because the direction that we travel in, the path that we take, will always be perpendicular to the force. So that means that any particle that comes into a magnetic field and feels a magnetic force will not change its speed. The kinetic energy that it has when it comes in is going to be the same at every point along the way until it comes out. And then if other forces act on it, then we can talk about changing the speed. But as long as it's only a magnetic force, there's no change in kinetic energy. So, what I want you to do, knowing that this is V cross B, let's talk about a couple of these things. These are more almost concept checks more than whiteboard problems. But I want you to take these two scenarios, these two particles, and the force acting on them, and knowing V cross B goes into that force, find what direction the magnetic field has to be pointing to create the force as described. Okay, so let's talk about these. So I'm going to take right-hand rule for each of these. But it's a little bit strange because we have the result in one of the inputs, but not the second input. We're going for the second input. But for each of these, I'm going to need to do some sort of strange contortionist act to try and make my hand go in the right direction. But go ahead and try and follow along with this thing. So I'm going to start with part A here. I'm going to say, okay, index finger should be pointing in the direction of V. Thumb should be pointing in the direction of F. I get something like this, and that tells me that my B field should be pointing out of the page. Because or the other way I could do is curling from V to B gets me a thumb that's pointing down. Now, part B is a little bit strange. Let me go ahead and draw this force. So F is going into the page. So let's go ahead and write that. So we'll say F is going into the page like this, and we'll just draw it slightly off to the side. Now, here's the problem. This one's a little bit different because we're not dealing with a positive charge. This equation right here, much like with the electric field, depends on the sign of the charge. We can't neglect that. Charge can be positive or negative, and if it's negative, it's going to flip a direction. So that says, even if F is going into the page, the result of V cross B is coming out. It flips direction with the negative sign. So what I really need to do here is I don't need to align my thumb with the force, I need to align it with V cross B. And in doing that, Say, okay, another contortionist act here. Index finger goes with V. My result, V cross B, comes out of the page. The magnetic field to make that happen should be going up in this case. And do be careful with those left hands. The question, is there a particular reason why the magnetic force is perpendicular to the velocity and field? I don't know my relativity enough to give you a 100% answer. Historically, the answer would have been that's just the way it is. Just like the electric force goes along the electric field, the magnetic force goes perpendicular to it. Historically, the answer would have been that's just the way it is. But my gut says there is something in relativity that would explain that. But I feel like that might be a general relativity question, and general relativity is a lot more difficult than special relativity. And I don't entirely know what the reasoning under that one would be. It's something to do with reference frames. Something to do with reference frames, but I'm not entirely sure. And the way that the field would change. That is a fantastic question, though. But yeah, I would say if you had asked 100 years ago, we would have all just been like, oh, yeah, it's just the magnetic force. That's what it does. But now that we have relativity as an experience, we can... I imagine that there is something under there that we could get out of it, but I'm just not entirely sure what that path would look like. Okay, so let's try another one here. We've got two different cases again, both of them negative charges this time. And what I want you to do, if we know that it's an electron, and we know what the velocity of that electron is, and the strength and direction of the magnetic field, I want you to find the magnitude of the force acting on each electron. And if you're feeling really confident with these, try to find what the direction is as well, or maybe in vector notation or something like that. Okay, so let's start taking a look at this one. So both of these, we're actually going to have the exact same answer. But let's kind of get into this piece by piece here. So let's start with part A. So I want to, again, twist my arm around. And like I play guitar, so my hands are flexible, but not that flexible. I'm going to go all the way this way if I can, and then I want to curl my fingers from V to B. That tells me that my cross product would be coming out of the page. But because I have a negative charge, the force is going to go into the page. So there's my force. And then what I can say is, okay, well, between V and B, that's a 90-degree angle, right? So the sine of 90 is always going to be 1. My force, if I'm just interested in the magnitude, I can just say, hey, that's E, V, B. 8 times 10 to the negative 13. Or 0.8 piconewtons. Now, B, you might be tempted to immediately jump into a determinant, but really, I can solve this out on the right hand as well, pretty well. And let me talk about why I'm going to say that this is the exact same magnitude as part A. My B field is pointing in the x direction. My velocity is currently in the yz direction. If x is supposed to be perpendicular to y and perpendicular to z, it should be perpendicular to the yz plane, right? It's like that surface normal kind of description. Here's my YZ plane, and then I've got my x-axis sticking directly out of that. So it doesn't actually matter what breakdown this is, whatever this angle could be. It could be 45, it could be 30, it could be 1, whatever it is. If that velocity is in the YZ plane and the B field is in the x direction, they are perpendicular to each other. That means that this exact same magnitude right here is, again, E, V, B. Same deal. The direction, that's a little bit more tricky. But this is still one that I can just do by right-hand rule in geometry. I can say, okay, we'll go from V to B. If I do something like that, then I would find my result, V cross B, should be pointing this way. And I know it's pointing exactly this way because it should be perpendicular to both input vectors. So that should be sticking out at a 45-degree angle so that this angle right here can be 90. And that's why I could say, even if it was a 30-degree angle or something else, I still know that they're supposed to be perpendicular. So I still know that it's supposed to be a 90-degree angle between V and V cross B. Now, the last trick that we've got here is we do have a negative charge to deal with, so I know that my actual force points like this, where that's 45 degrees. So, one of the things that I want to make sure that we don't get too tripped up on is thinking about which direction is positive on a graph like this. And this is a little bit of a strange point, I know at first, but where we have the axis indicated, X, Y, and Z, that's the end that's positive. So in this part right here, in part A, what we would see is that we have a positive XB, but a negative Z velocity. So at the end of the day, the force that I get is a positive Y. The three axes are related by the right-hand rule, and that's why you can't necessarily just draw them out willy-nilly. They're always going to be related in some way like this, right? If I've got X cross Y is equal to Z, and we can line up our hand and we would see something like that, we could do some other combination of them, but they're always the three related by the right-hand rule. And that's what keeps everything graphically making sense. If we don't have that, then some stuff gets a little bit funky, and there are ways to deal with that, but like cross products don't work in the same way anymore, and it's not worth the hassle. Your three axes should always line up in some way with the right-hand rule. And I always just remember X cross Y is equal to Z. So, because if you're going through the determinant method, you need to be careful with that. You need to make sure that we're putting the positives and the negatives in the right spot, because you'll find the same magnitude no matter what, but which ones are positive and negative might change, depending on how you've got that written out in the first place. All right. Well, let's take a look at this one. Here is a classic problem that we have seen before. We are launching some sort of charged particle through a parallel plate capacitor. Again, I'm assuming just for fun or something because we keep consistently doing this. But as we launch it through, this time around, we don't want it to hit either one of the plates. We want to make sure that it goes all the way through without any sort of deflection. To do that, we're going to introduce a magnetic field into this thing. Not railguns yet. Railguns soon, not railguns yet. So, what kind of magnetic field do we have to make sure that this thing doesn't get deflected from the trajectory that it's on? All right, let's start taking a look here. So, before we write down any numbers or anything else, I really want to see how much we can solve out for this thing. So, what we're looking at here. We know that the electric field is going to pull in some direction, and we're going to talk about that one first because realistically we're more experienced with it. We know how the electric field works at this point. We know what direction it goes. We know where the electron wants to go, right? It wants to go towards the positive plate. So let's start with that. Let's say, okay, well, I know that there's going to be an electric force pulling me this way. Then if I want to make sure that I'm not getting deflected, that I'm able to pass right through this thing without any sort of collision, any sort of deflection, I need to have zero net force. I need to have a magnetic field going this way. Not a magnetic field, a magnetic force going this way. The field remains to be determined. Okay, so now we're also dealing with an electron, right? A negative charge means that I know V times B, or V cross B, should go this way, right? The negative sign would have flipped that from the charge. To get V cross B to go up, think about right-hand rule. I need to go from here, curl which direction to get this? I'm going to need to curl towards inside. Into, whoops, that's not into the page is my B field to make this force happen. And I wanted to go through this to establish a lot of our direction stuff because this really is half the battle. Now that we know what the direction looks like, I'm only going to think about the magnitude from here on out. So what I'm going to say is that I know the magnitude of the electric force has to equal the magnitude of the magnetic force. If not, then, you know, mission failed. Okay, what goes into each of these? It's been a little while since we've looked at these, but we might remember. So the charge that I'm looking at is fundamental charge, E. And again, I'm just worried about magnitudes here. I'm not thinking about direction because we've already solved that part. Thinking about magnitudes, all my numbers are positive. E times E is equal to EVB. Don't need that. Solve this thing out. What magnetic field do we need to have? B is just going to be E divided by V. Well, fantastic. We've got V. Now we just need to find E. And that should hopefully be a pretty quick thing because we know that between these two plates is a potential difference of 200 volts. And because we know that between a parallel plate capacitor, we have a uniform electric field and a constantly changing, a linear potential gradient, that says that E must be equal to delta V divided by the separation between the two plates. 200 divided by 0.01 is 20,000 volts per meter. For my strength of the electric field, we plug it in with my velocity, and then I always get this mixed up. Is it 0.002 Tesla as my final answer? So, there's some neat things you can do with this stuff, right? Seeing how a particle would interact with a magnetic field, we've got actually some particular motion that we might see when a particle is put into a magnetic field. One of the big ones is what we call cyclotron motion, right? Cyclotrons being things that cycle charges around in a big circle. If I have a particle with a velocity perpendicular to the magnetic field, then the magnetic field is going to exert a magnetic force perpendicular to both. If there's no friction or nothing else kind of going on here, if the magnetic force is the only one acting, then what we expect to see then is actually circular motion out of our charged particles. Because my right-hand rule will constantly be changing. If my velocity goes one way and my magnetic field goes another way, then I'm going to see constantly as I oscillate around that circle, the force is always pointing towards the center. And if the charge is flipped, that's fine, because now everything just flips in direction. And instead, it would go around the other way. Because in this picture right here, we are assuming that it's a positive charge, but if it were to be a negative charge instead, then it would just go in clockwise motion rather than counterclockwise. And we can pull a few different things from our old equations for uniform circular motion. We know what the force is that's creating this centripetal force to keep us in the circle, and knowing all of that stuff and the conditions we need to keep that uniform circular motion, we've got two different equations that we can pull out. The radius, that was supposed to be an arrow, the radius of our cyclotron motion, the radius of our oscillation, is going to be this. And we also have the frequency, or how many times per second does it spin around. And we're going to prefer frequency to period here, because realistically, if we're dealing with electrons, the period is going to be like nanoseconds. It's not going to be big. So frequency is a little bit easier to discuss oftentimes. But these are two new equations that we can look at specifically for when we have a charge in some sort of uniform magnetic field. So let's try this out. Let's imagine some radio astronomers have picked up a signal. They're scanning through different infrared frequencies, and they find something right at 45 megahertz coming from some nearby gas cloud. They think that there is some magnetic field to this, and a bunch of electrons are spinning around in cyclotron motion because of that magnetic field. Oscillating charges emit light, so they assume, okay, well, they're probably oscillating around back and forth like this, and since we're getting a signal at 45 megahertz, we can assume they're spinning around at 45 megahertz. What is the strength of the magnetic field to make this happen? Okay, let's start taking a look here. So, what we've got here, it's like as close to what we could say is textbook cyclotron motion as we could possibly get. The assumption here is that the frequency that we're given, 45 megahertz, is the same as the frequency of the oscillation, which does make sense. That's a reasonable assumption to make, assuming that it's electrons spinning around that are making this in the first place. But that's all pretty reasonable to me. So then, what we're expecting to see is actually not too much. What we would say is, okay, well, if I know the frequency to be 45 megahertz, which is 45 times 10 to the 6th hertz. Okay, well, now I just need to put that into my cyclotron motion equation. I can say the frequency we could have found from Q times B, not E, B, divided by 2 pi m. Knowing here that the mass, since we're dealing with electrons, the mass is 9.11 times 10 to the negative 31st kilograms. The charge, and again, I'm only going to focus on magnitudes here. So 1.6 times 10 to the negative 19 is the magnitude of the charge. And I'm only concerned about the magnitude because if I put a negative in here, I would find a negative B field, and that only makes sense if we have a direction. And I don't know what the direction is, right? We don't specify. We just know that we're getting some sort of oscillation, some sort of signal. So the rotation is going in some direction, but which direction, it doesn't really matter. Rearrange this thing. Oh, not Q times B. I keep doing that. Divided by Q. Plug in all of our numbers here, and what we should find at the end of the day is 0.00161 Tesla. Or 1.6 millitesla. And that's what we've got. Let's keep moving right along. So there's some neat things that can happen with this, right? And I keep specifying that this is in a circle and everything else, but it doesn't strictly have to be circular, right? What we're really trying to say here is that in the presence of a magnetic field, particles will tend to kind of spin around, right? They like to spin around those magnetic field lines. If we have a little bit of velocity going in the same direction of the field, we'll create kind of like a helix shape. And this is especially apparent when we're talking about something like the Earth's magnetic field. I know I brought this up last time, but when we have a bunch of charged particles coming from the sun, they get deflected. Now we know how, but they'll come in, and they're coming in at maybe a slight angle or something like that, or maybe they're coming in not directly perpendicular. But as they start to see that magnetic field, they start to spiral around the magnetic field. And as they spiral around the magnetic field in one direction or the other, they'll fly off to the sides, and they'll follow those field lines. And then those high energy charged particles collide with a bunch of different things in the upper atmosphere and emit a bunch of light, right? That's essentially what happens when you have high energy collisions. A bunch of light gets produced from that, and that's what we see as Aurora Borealis. So it's a pretty cool thing, right? I think it's, honestly, it's not something that I have seen with my own eyes, but I think it's a fascinating thing that it's one of those, I don't know, there's a lot of things that go around it. I think it's got some sort of impact on humanity, I think. It's kind of a fascinating thing forever. It's been up there. But here we are able to explain it, able to pick it apart and discuss what really makes it happen. I just think that's kind of fascinating and neat. That's some fun bit that we would have. Would other planets in our solar system have auroras in the same way? It depends on whether or not they would have. So you need two things for it. You need either, you don't need either. You need both. You need an atmosphere, and you probably should also have a magnetic field that's strong enough to divert some of those particles. As I was talking about last time with Mars, Mars does not have a strong magnetic field and it has very little atmosphere. So I wouldn't expect to see much of anything on Mars, but maybe some of the other planets perhaps. I don't actually know for certain on that one though. If they've got a strong magnetic field, you might see some sort of aurora there. But part of what makes it so strong on Earth is that a lot of it, you can kind of see from the picture here, these particles get funneled up into those spots because that's where the field lines are emanating out of. So if it's following the field lines the entire time, then a lot of these charged particles are getting funneled to these places in particular. So because you might be able to see like a very, very light aurora without a magnetic field like that, but you would still need to have a thick enough atmosphere to cause those kinds of things. Yeah, I could believe some of these other places might. I don't know a ton of details about other planets though. Astronomy has not been something that I've been particularly interested in for a long time. Oh, I don't know. Does it have a magnetic field because of the rings? I don't know, actually. I mean, I guess it is a bunch of spinning rocks, so it would probably create some sort of magnetic field. I don't know. I don't know. I don't know what causes rings around planets, actually. I don't know if that was... I assumed it was always gravity, but, yeah. I don't know. I'll have to look into that. I don't have a good answer for that one. So maybe ask about that again on Friday, and I'll hopefully have an answer then. I can talk about that a little bit more. But anyways, it's kind of neat, right? But it's what's causing some of these different particles to fly around in every which direction, and, you know, a bunch of different spinning that can happen and stuff like that. So let's scale this up a little bit. Let's no longer just think about one single particle experiencing a magnetic force. Let's think about what happens if a lot of particles start to experience a magnetic force, right? And the way that we're generally going to do that, it should come as no surprise, is to think about current going through wires that are going to be experiencing a magnetic force. So, just like the argument that we made for the Biot-Savart law, remember that we essentially took our single point charge equation and then messed around with it a little bit so that it worked with current instead of just a moving charge. We can go through the exact same steps to end up with this equation down here. That is to say, a little tiny piece of the wire would experience a little bit of force, and that would be equal to the current going through that piece of wire times the length of the wire crossed with B, where the direction is the direction of the current. And then if we wanted to find the total force on the entire wire, we would just integrate that. So if the magnetic field goes in weird, non-consistent directions and the wire goes in weird, non-consistent directions, this would be a very difficult problem to solve. But most of the time, we're going to focus on things that are much easier. So in the case where we would have a straight wire inside of a uniform magnetic field, that integral would simplify to this easy thing right here. And sometimes I go back and forth on this. I am not a huge fan of the notation where L is the vector because I don't think it makes much sense. I know current is not supposed to be a vector. I know that. But I like to write I vector anyways. I think it makes more sense to me. And since I'm not reading any of your work or anything else, you're welcome to use either one. But I think it makes more sense to me to make current a vector, even though I know that's like they should put me in physics jail or something for that, but it makes more sense to me. That's the way that I like to think about it. In any case, the direction is always the direction of the current. Whichever one you have, maybe you just extend the vector, so it's the IL vector. However you do it, it's the direction of the current that matters, because that's the direction that the charge is moving in. So, you can bend the wire, yes. And that would be, you'd probably have to think about the integral at that point. So, let's take a look at this problem here. Before you get involved with any numbers or anything else, what I want you to do is I want you to look at these 3 pieces of wire that have a magnetic field that's going to be acting on them. Think about the direction of the force acting on each wire. And then, once you've got that, and you can figure out if there's anything that cancels or what's going to sum into our net force at the end of the day, then start plugging in numbers to calculate what you need at the very end. Okay, let's start taking a look here. So, first things first, I want to find each direction. So let's take this thing. Let's think about what's going on with each piece of the wire. And I'll do this in red. So, right-hand rule, before I can get into that though, I need to know what direction the current's actually moving, right? But this is a really, really simple circuit. So I can look at this and I can say, hey, there's no crazy loops, there's no multiple batteries or anything else. I can kind of just look at this right off the and say, hey, current goes this way. And that's that. Let me get back to current later. So each piece of the wire is going to have a current going this way, current going this way, current going this way. Then I'm going to need to take I cross B, right-hand rule here, says, okay, I cross B, I'm going to get a force pointing up for my top wire. So this wire has a force going this way. This wire down here has a force going this way. And this is why I said draw out the picture first, because the fact that we're not given any sort of horizontal direction or horizontal length was on purpose. We didn't need it. Those two parts are going to cancel out regardless. Now, the long wire to the right is going to experience a force though, and we can kind of sense a trend here that these are going outside of the circuit as it's drawn currently. But a right-hand rule would tell me the exact same thing. If I'm trying to point this down and my magnetic field is going into the page, then my thumb kind of comes out like this. I don't even know if that's visible or not. I'm trying my best. My arm only has so much flexibility though. My force should be going this way. So these other two I don't need to worry about. I'm just focused on this one right here. And that's going to make everything a little bit easier to think about. Because now that I'm solving out for that force, I'm going to say, okay, force would be equal to, here's my double IL vector, because whichever one we pick, it doesn't really matter, crossed with B. But these things are perpendicular anyways, right? And I'm just worried about the magnitude. I've got the direction covered already, so I'm just going to write this out as F is equal to ILB. L is 10 centimeters. B is 50 millitesla. I we need to find that real quick, but this is a simple circuit. So I can say delta V is equal to IR. I should just be 5 amps. 5 amps of current, 0.1 meters, 0.05 Tesla. At the end of the day, we should find that the force is 0.025 newtons. And that's all we've got. Okay, so let's look at another one here. And this is kind of a fun one. I know you have an equation for this on your equation sheet, but I don't want you to look at that. Or even if you do, you know what answer you're going for. Prove that it works. Let's imagine we have two very long wires, and they each have a current going through them. What is the force on one wire because of the other? Like maybe we focus on wire 2. What is the force on wire 2 because of wire 1? Okay. How's about we start taking a look? So, as I've got this thing, I'm looking for a force. As I'm looking for some sort of force, let me start there. I know there's going to be a magnetic field acting on wire 2. I'm looking for the force on wire 2, so I know there's going to be a magnetic field acting on it. So we say force on 2 is I2, because the force acting on the charges moving through wire 2, L cross B. Now, where does that B field come from? It's not wire 2 acting on itself, because objects don't exert forces on themselves. It's the magnetic field from wire 1. So I'm going to label this as B1. So we got force 2 from B1. Now, let me think about what direction that's going to go. If I use right-hand rule here, I think about what direction is the magnetic field going to wrap around this wire. I can use the right-hand rule, align my thumb with the current. Current should wrap, or not the current, the magnetic field should wrap around as my fingers wrap around. That is to say, we would have up top, it would be coming out. On the bottom, it's going in. And on the sides here, you know, kind of outside of the picture and into the picture, if we were to see that, or in front of the wire and behind the wire, we would see vertical field lines. But I'm not going to be super concerned about those. I guess I could kind of draw, like, here's what one would look like, something like that. But I think that's going to kind of clutter up our picture a little bit too much here. But I'm interested in this, and I drew this out in the first place because we can kind of see here that the field lines from wire 1, at least where wire 2 is at, are going into the page, whereas current's going in the x-axis. Those two are perpendicular to each other. If they're perpendicular to each other, then I don't have to worry about this cross product. I can just focus on ILB. I2 times L times B1. No more pesky vectors to worry about. So then the only thing comes, we need to just figure out what B1 is supposed to be. And what I'm going to do for that, I'm going to think, okay, well, these are supposed to be long wires. And on top of that, I can kind of see they're not super far away from each other. They're pretty close. I'm going to take an approximation here, and maybe this is a little bit sloppy, but I think it's a lot easier. Take the approximation that it's an infinitely long wire. If we do that, then B1 come on. There we go. Let me steal the color from this thing. B1 would be equal to mu naught I1 divided by, where did I lose this thing? 2 pi, and then I would put r in here, but really the distance that we're looking at is what we've got labeled on our picture as d. So mu naught I1 over 2 pi d. That's my expression for the B field. Let me plug that thing in. And I'm going to try and justify this. I'm going to say, hey, well, look at this. The wires are pretty close together, and I'm going to say that probably from around here up until here, my infinite wire approximation works really well. And maybe on the ends it doesn't work quite as well, but it gets us most of the way there, and it's a lot simpler. And why would you want to do the integral unless you don't have, like, unless you absolutely have to do the integral? Take the approximation. We get most of the way there. So when we plug this in, the expression that we end up getting, mu naught I1 I2 times L divided by 2 pi d. And we can check with our equation sheet to show that that is the exact same equation that we should be seeing in our force between two parallel wires. But that's what we've got. So how are we feeling? All right. Now, one thing that I haven't specified here is what direction this would be going. And generally, when we're talking about parallel wires like this, we've really got two circumstances, right? They're either going in the same direction, in which case our right-hand rule would actually, and let's go back to our picture to confirm this real quick. But if I'm looking at what's the force on wire number 2, I'm going to say, okay, I cross B, and then I get a force pointing towards wire 1. Wire 1 experiences the exact same thing, but the force points down now instead. So it's an attractive force between those two. The wires are going to want to cling together. In the case that they're going in opposite directions, well, the force is flipped too, right? So now they're repulsive instead. But this is an easier thing to solve with geometry than it is to solve with cross products because they're two parallel lines. It gets a little bit tedious to talk about some of these vectors sometimes if we're not just look at the picture, right? Use geometry, use the right-hand rule. That'll help and make this whole thing a little bit faster and easier. So, talking about forces, of course, our discussion moves to torque. And this is actually not super bad or anything else because what we have here, this demo is done in the text. I do recommend kind of looking through that. I know you should have looked through it already, but maybe with a little bit more insight, take a look at that again and see if it makes any more sense the second time around. But anytime we have any sort of magnetic dipole, what we've really got here is if it's in a magnetic field, it might experience a torque, right? And that's a pretty easy thing to write down because that torque is just mu cross B. So any sort of dipole, but most of the time we're looking at current loops or anything like that. But that's what we find, should you need that for any sort of problems. And our last problem for the day, and probably the most fun here. Let's build a railgun. How do we do it? Well, I'm going to have two guiding rods, and I'm going to have one wire in this orange gold color over top that's going to have some current running through it. I put some sort of permanent magnet beneath this entire thing so that I have a magnetic field here. A current with a magnetic field is going to experience a force. Your job is to first calculate or figure out what direction do we need that current to go so that it fires that way and not into us. And second, using these variables that we've got, L, M, B, and I. Oh yeah, I did say M. What velocity should we be getting after this thing is launched? Okay, let's start to take a look at this one. So, there's some specifications that make real railguns a little bit different from this, but the general principle is there, right? And this is one that you could probably reasonably create with You know, you don't necessarily have to have all the tools at hand, but you could reasonably create a lot of this yourself if you wanted to try this thing out and experimentally test our predictions. Disclaimer, I'm going to say don't do this just in case anything bad happens, but it is a cool project. So, first things first, we want to make sure that this thing launches the correct direction. Not at us, away. That means that the force from where it's starting, we don't want it to go here. This is bad, right? None of that stuff. We want the force to go this way so that it launches along the rails and picks up plenty of speed while it does so. Okay, with all of that in mind, one thing I am going to do real quick, I'm going to change this. Let's make this a capital L instead of a lowercase l, just so it's a little bit more clear. So we need the force to go this way. This is kind of like our first whiteboard problem of the day, right? We say, okay, well, the force needs to go that way. The B field needs to go up. So my current needs to go this way. Now, current cross B will give me the force that I need to fire off. So this actually runs into a little bit of an issue as well, and I don't know if anybody has caught on to this one, but most of these things used to have, they need to have some sort of guidance along with them. Because think about what happens here. As this thing starts to accelerate, now we don't just have moving charges going along the direction of current, we've got moving charges going forward because the whole thing is moving forward. And that motion is also going to experience a force. Do not use your left hand. So that's one of the little tricky parts on this one. So what we're going to say here is let's imagine that we've put some sort of fencing on the side of this thing so that it's not just flying off to the side partway through, that it stays in place going along the rails the entire time, right? They're guiding rails for a reason, which should guide the projectile out. Okay, so now that we have that, we need to think about this. What happens to the force? As I go down the rails, what happens to the force acting on our orange bar here? What do we think? Is it constant? Is it changing? Is it changing direction, magnitude? What's going on with it? What do we think? Constant. I agree with that. I think it should be constant because if I think about what happens with this thing, let's look at this. Let me write out this equation. I, L, cross, B. The B field is uniform. The direction of the current doesn't change. The wire moves, but the direction that it's moving in doesn't change. So I can expect that this force is going to be constant all the way along the rail. And now this opens up a couple different possibilities for how I might solve this problem. Right, I also know that because it's perpendicular to the B field, I can really just write this out as a magnitude, I, L, B. So with that in mind, I think the easiest way to think about this is not actually in kinematics. That might be our first instinct to say, force is equal to ma, and then do some kinematic stuff. But I think that's a little bit more complicated here. Instead, the magnetic field can't do work on moving particles. However, we've got some current moving through this piece, and there is work to be done by this force with something else pushing this current for us. Right? This is an opportunity to get some work done. And I want you to kind of know that distinction here, because if it's just a random particle flying through, the magnetic field will not do any work on it. But in a case like this, there is the possibility for that to happen. So, with all of that in mind, what we can say then is that, hey, it's a constant force acting over a distance d. The work to be done is F times d. The work to be done is going to be converted into kinetic energy at the end of the day. I, L, B, D, I think they rate movies or something, is equal to 1/2 mv squared. Solving out for v, we get this right here. That is our expression for the final velocity of our projectile. Ramping up current, ramping up the B field, and increasing the length of the guiding rails could all increase my velocity as we launch this thing out. Railguns, indeed. There are a lot of fun things, and this is not a very, very difficult thing to make. Like, if you wanted, like, a coil gun, that's a little bit of a different story because you have to have, like, sequenced pulses of the magnetic field, and that's a little bit tricky. But a railgun like this is actually really easy to make. You know, it's not going to be good, but, like, it's not the point, right? If we're building a railgun at home, the point is not to make a good railgun. It's to make a railgun at home. The rails, so in a case like this, I haven't really quite specified how we're getting current through the orange wire. In a real railgun, you would use the rails to carry the current. So they would want to push each other apart because you would want to have current coming in like this and going out like this. So the rails would want to push each other apart, but if you look at like actual configurations of railguns, this is all in like a tight casing together. You usually have your projectile sitting in the middle between these two, and it's connected. You turn on the power and it launches out, but you have a thick casing around the rails to make sure the rails don't fly apart, and you also have the projectile in between the right rails so that when it's actually flying, even though it's going to experience a force going to the side, it stays on track. But I think we'll call it there for the day. So, thanks for being here, everyone. And I'll see everyone next time. Have a good one.